Hello again, everyone. Welcome to our discussion of section 3.1, where we will focus a little bit more on the properties of the quadratic function. Okay, so quadratic function usually looks either like this or the other way around, so something like this, or we might have a graph that looks like that. Okay. Of course, there are horizontal versions of this too, and we will look at those horizontal versions in the trigonometry course. If you ever have to take the Math 127 course, you will see the horizontal version of this in that course. But for the graph of a quadratic function, this is a typical look that we have, and it's a curve like that. And either, if you have this kind, the topmost point of it, it's called the vertex, and in this case, the very bottom of that curve is called the vertex. So that is the vertex here. So you could have a high point or a low point, a maximum or a minimum. Okay, and if the arms of this curve intersect the x-axis, those are called the x-intercepts. So that's one x-intercept on this side, and that's another x-intercept on that side. Okay? And in most books that I've seen, the authors of the textbooks like to refer to that vertex with coordinates with letters h comma k. So this is the same thing as the x comma y coordinates, but when those coordinates refer to the vertex of a quadratic graph, then they call them h comma k. Of course, I want to very quickly remind you to please, if you haven't done this already, skim through the textbook section 3.1, or spend half an hour to 45 minutes reading through the section, take a look at the examples and everything. Then attend the class or watch this video and take notes, and then review your lecture notes and solve all the problems you see in the book or these series of videos on your own without looking at the solution. And with the videos, it's really easy, right? You just pause the video, solve the problem on your own, and then you look at my solution. Number 4, complete all the homework assignments by the due date and review for the entire semester. Okay, so that approach, as I said earlier in the course, is the way to study all quantitative courses, not just this course. Okay. All right, so the quadratic formula, which is used to program in computers or manually calculate the coordinates of these x-intercepts, is that formula. So this is known with that name, quadratic formula. Okay, it's simply coming from the coefficients of the quadratic function in this form, written in this form. So the coefficient of the quadratic term x squared is a, ends up there and here. B is the coefficient of the x term, not x squared term, but x term. The coefficient of that term is b. And c is the constant value if there is one. If there's no constant value, it's simply 0. Okay. So finding the coordinates of the vertex, this is something that is very, very important, especially because that vertex in application problems, or otherwise known as word problems, that vertex means something. Because first we said it's maximum or minimum, so it represents the maximum or minimum of something. For example, if you have a cost function for your business, then you naturally want to minimize that, right? So you're interested in if the cost function you're dealing with is quadratic in nature. If it's not, then you wouldn't do this. But if your cost function is a quadratic function, then you're interested to find the minimum point. Where does that happen? how many products manufactured and how many sold generates the minimum cost. Or if you have a profit function, on the other hand, if you have a profit function that is a quadratic function, you naturally want to maximize that for your business. So you're looking for, again, you're looking for the coordinates of the vertex, which would be a maximal. Okay, so that coordinates of the vertex can be calculated using this formula. So for the x value, and x has a meaning in an application problem, in a word problem, x would have a meaning, and then is equal to minus b over 2a, and then the y value is simply whatever you find as that x quantity, you put back into the function like that. The function evaluated at that value gives you the y value. Okay, so in the case of a profit function, if you're maximizing, so that would be the profit, and this would be how many units of products or services do you have to sell to achieve that profit. Okay, so what I mean is that in the real world, these numbers have a very useful meaning to them. Okay, so the standard form. And before we go to this, I just noticed, by the way, please make sure you read all this, because these worksheets are not just examples, as you notice. They are also excerpts of important content that you should know. So I've tried to summarize the content of the book in order to put emphasis on the most important content from your textbook. So here, above, let me just explain what this means, this short paragraph means. So here, I gave this little example here, little graph here, that you can have either this kind of curve for a quadratic function or this kind of curve for a quadratic function, right? So how do you know, is there a way to predict which kind of graph you're going to have? Yes. So in this quadratic function equation, this one that I boxed, if that coefficient is some negative number, -1, -2, whatever negative, then that means you're going to have a curve that is upside down like this. And naturally, if you have a curve that is upside down, you will have a vertex that is a maximum point, right? You're not going to have a minimum if you have a curve like this, right? With a curve like this, you're going to have a maximum. How do you know you're going to have a curve like this? That coefficient A must be negative. On the other hand, if that coefficient is positive, anything positive, then you're going to have this kind of curve. Okay? In that case, you're going to have a minimum point, because the way the curve looks, you can only have a minimum point, never a maximum. Okay, so the coefficient of the quadratic equation there, or the coefficient of the quadratic term, x squared, will tell you whether you have this kind or this kind of graph, whether you have a maximum or a minimum point. Okay, so that's what this paragraph is talking about. So the standard form of a quadratic function, the standard form, has this look. So it's written this way. And it's very, very useful, because you already know, if you show me a quadratic function that is written in this form, you already know where the vertex is, right? Because the vertex is located at h, comma, k. And remember when we were talking about the transformation of functions? Remember those general functions that we had for the square root function, absolute value function, the quadratic function? Remember all those? So if this is ever positive, say x plus 2, that means that h must have been negative 2. Okay, so minus 2 will make that minus positive. So this goes for that. This is very, very similar to the way we used to interpret the general functions when we were talking about the transformation of functions. Okay, this is very similar to that. And we'll see examples of it anyway in a few minutes. Okay, so here we have a quadratic function. So right away, a is equal to 1, b is equal to 4, and c is equal to 0, right? The constant is missing. So I just wanted to write that down just to exercise with all these different things we should notice when we see a quadratic function. We should notice that immediately. Okay. It says, express the quadratic function in a standard form. Hint, use the method of completing the square. Okay, so let's do that. Completing the square for this, we learned how to do that, right? So we have, first of all, we can apply the method of completing the square immediately without factoring. Why? Do you remember why? Because the coefficient of the quadratic term is positive 1. If it was 2 or 5 or anything, we would have to factor it out. But we don't have to factor anything. It's positive 1, so we can immediately start the procedure for completing the square. So the completing of the square method says, if the coefficient of the quadratic term is positive 1, whatever b is, b in this case is 4, divide that by 2. Do you always divide by 2? Yes, you always divide by 2. Once the coefficient of the quadratic term is positive 1, the b term, you always divide it by 2. So if we divide that, so divide that by 2, and we get 4 divided by 2 equals 2. So we can immediately complete this square by saying, and this is 4, by immediately saying that x plus 2, that 2 is that one. If we had minus 2, if this was minus 4 divided by 2 equaling minus 2, then I would say x minus 2. Okay? So in this case, it's positive 2. X plus 2, parentheses, squared. So I've solved one problem, but I created another problem. What problem did I solve? The problem I solved is now these two terms are part of this perfect square. How do we know that? Well, let's expand this x plus 2 squared. I'm going to do that on a piece of scratch paper because I don't have much space there. So let's expand this. You can FOIL it. If you don't, I'm going to use the special product formula because I remember it, and I've encouraged you strongly to remember it. But if you don't remember it, you can still manage it. You can FOIL it. You can do it like that, and it'll take you a few seconds more, but you'll get the right answer in the end. But I'm going to use the special product formula. So expanding this, we have x squared plus 4x plus 4, right? Compare this with what we started with, right? Is that the same thing? We have x squared. We have 4x, 4x. We have 4 here. In the expansion of this, we end up with an extra 4. So that's the problem we created. Is there a way we can solve this? Because we don't have a 4 there. We have a 4 here. Is there a way to solve that? Yes. We simply say minus 4. Minus 4. Okay? Now when you expand this and you say minus 4, these two add up to 0, you end up with what you started with. So that's the method of completing this square. So now we have expressed the quadratic function in a standard form. Compare this with this. Let me put this side by side so you can see them. This is on the previous page. Compare what we have here with that. So, and then part B says, let me move this up so you can see it. Right there, right there, like that. So compare this with that. And then part B says, find the coordinates of the vertex. So we know that the vertex is at h comma k, right? Compare this with that and tell me what is h. What must h be then? Compare this with that. H must have been -2, right? And k must be equal to, compare this with that, k must be equal to -4. So that's the coordinates of the vertex. So you can, if you have the quadratic function expressed in the standard form like that, you can immediately know what the coordinates of the vertex are. But if you have your function like this and somebody asks, what are the coordinates of the vertex? You have no choice but to apply this formula. No choice. Then if you don't want to complete this square, but you want to know what the coordinates of the vertex are, you cannot, then you have no choice but to apply this formula to find the coordinates of the vertex, which means you're going to need to know B and A, right? B and A. So you say minus B over 2A, it's going to give you the X component, then you will, whatever that value, you plug it back into this equation and you find the Y value from it. And we have examples like that too. They'll come up. Okay, so what else they're asking? They're asking, find the coordinates of the intercepts. Okay, the coordinates of the intercepts are, we can apply the quadratic formula. We can do that. Let's see. But in this case, it's even actually easier. Okay, so you can just factor this. We can factor this. We don't even have to use the quadratic formula. You could, if you want to, that's another way. But because this expression is so easy to factor, we don't have to use the quadratic formula. So f of x equals x squared plus 4x equals x times x plus 4. So I factored this out. So for x-intercept, and let me move this up so it's, so that's our function which I factored. So for the x-intercept, then y or f of x equals 0, right? Y equals 0, or f of x equals 0. Y and f of x are equivalent. So these two are equal to 0, so then let's find x. So 0 equals the factored form x plus 4. Now, because of this, we have x equals 0. If this product is equal to 0 by zero product property, which we saw in chapter 1, then we can find each factor. We can set each factor equal to 0 and solve for x. Minus 4. So the x-intercepts, let me make this plural because there's two of them. The x-intercepts are 0, 0, and from this, -4, 0. Okay, now the y-intercepts, or the y-intercept. For y-intercept, that means that x must be set equal to 0, right? Any point on the y-axis has its x value equal to 0. So that's the condition we have for finding the y-intercept. Then in the original equation, let's substitute for x with 0. What do we have? We have 0 squared plus 4 times 0 equals 0. Therefore, the y-intercept, we have 0, 0, which is the same thing. So which makes sense because the graph, it means that the graph is intersecting both axes at the same location, which is the origin. Okay, the only place where that can happen at the same time is the origin, right? Okay, so now we have the intercepts. So these are the x-intercepts, that, and this is the y-intercept right there. Okay, so draw a rough graph of the function very well, because we have all the information we need, right? So the coordinates, the vertex of the quadratic function is at that point. This is very important. -2, -4. Okay, so let's find that. -2 would be here, and -4 is right there. So that's the vertex. Now, let me ask you this. Let me write this function here because it's off the screen. This is our function, f of x equals x squared plus 4x. So looking at that function and knowing that that's the vertex, right, that is our vertex. Can you tell me if that is a minimum point or maximum point? Looking at that. We explained it a few minutes ago, right? You should be able to predict whether that vertex is a minimum point or a maximum point. Well, if the coefficient of the quadratic term is negative, if it's negative, which is not, if it's negative, it would be a maximum point because the curve would be like that, upside down. But when it's positive, it has to be a minimum point. Okay, we already know, before even drawing the graph, we know that the vertex is a minimum. Okay, and it has coordinates -2, -4. Right? We know that. So, what else do we need to graph this function, this quadratic function? We need the intercepts, of course. One is that 0, 0 is both the x and the y-intercept, right there. Oops, sorry, I was off the screen for a second there. So I want to show you, okay, there we have the x. So we have the x-intercepts and the y-intercept. So there is one, x 0, 0, 0, and then this one, that's an x-intercept. -4, 0, which would be this point. So let's try to connect these points with a smooth curve, if I can. Like that. Like that. Mm-hmm. So that's a rough sketch of that quadratic function. Okay, so in this example, number 2, this number 2, before I go ahead and solve these 2 and number 3, please make sure you download the blank worksheet and write down your own solution before you unpause the video and see my solution, okay? I'm counting on you that you're doing that. Okay, so given this quadratic equation, is the vertex a point of minimum or maximum? Can you predict that? Yes, we can, because the quadratic term has a negative coefficient. So if it has a negative coefficient, that means the graph of this function is going to look like that. So if because of this negative, because of that, the graph is going to look like that. Okay, it's going to be upside down. So this point is going to be a maximum point, right? So is the vertex a point of minimum or maximum? It is a maximum. Okay, we know that just by looking at the equation like that. Then it says find the coordinates of the vertex. Well, the coordinates of the vertex, notice there are 2 ways of finding the coordinates of the vertex, right? One is using this formula. if you have your equation given to you like that, then you can find the coordinates of the vertex using this formula, which we will use in this case. Or if you want, you can also use the method of completing the square, just like the example we just did a few minutes ago, and rewrite this equation in this form, which will tell you what the coordinates of the vertex are, h and k. So there are two ways of knowing what the coordinates of the vertex are. One is using this formula, or complete this square, and from the standard form, which is that, you know what the coordinates of the vertex are. Okay? All right. So in this case, we're going to use this formula, which is, let me write it here so we can look at it as we go through this. Okay? That's the formula we have in that first page. So we need to know what B and A are, right? So let's, A is -1 and B is +1, right? So let's find the x component of the vertex. So x equals -b over 2a equals -1 over 2 times -1, right? 2 times -1. So what do we have? We have -1 over -2. Minus times the minus, we get +1/2. So that's the x component of the vertex, right? We already know the vertex is a maximum. Okay, so now how do we find the y component? Well, we take whatever -b over 2a was and replace in the x to find the function value at 1/2. Very easy, right? So the function at 1/2 is equal to minus, I'm just replacing x with 1/2, minus 1/2 squared plus 1/2 plus 1, right? What do we end up with? So so that's our x, okay? So now we're finding the y component of the vertex. So we have minus 1/2 squared, that's minus 1/4. Then we have 1/2 plus 1, right? So we have to take the common denominator here. What is the common denominator? It is 4. So this first fraction, minus 1/4, right? Do we have to multiply this by anything, the denominator by anything? No, it already has a denominator equal to 4. So we leave it alone. This 1/2, do we have to multiply it by anything to get it to 4? Yes. We have to multiply this by 2 to get it to be 4. But hey, we can't do that to the denominator and not do the same thing to the numerator. So let's multiply the numerator by 2 as well. Okay, how about this? Yes, the denominator here is 1. We need to make this 4. So we got to multiply the denominator by 4, times 1 is 4. But we can't do that to the denominator and not do it to the numerator. So 4, multiply the numerator by 4 as well. Okay, so what do we end up with? The first fraction is minus 1. The second fraction is 2 times 1, positive 2. The third fraction is 1 times 4, or positive 4. Okay, so we end up with -1 plus 2 is positive 1, plus 4 is 5, 5 over 4. So this is the y, this is the x. So h comma k, or the coordinates of the vertex, which is equal to h comma k, is equal to is equal to 1/2, which is the x component, and 5/4. Okay? Like that. So that's the vertex. And we know it's a point of maximum. Okay. I hope this agrees with your own solution. Okay, so this one, once again, I hope you've had the chance to solve this on your own, and you're now waiting to see my solution. So, is the vertex of this quadratic function a minimum or maximum? Well, take a look at the coefficient of the quadratic term. Is it positive or negative? It is positive. So you know, because of this term, it's positive. That means that the graph is going to look something like this. This graph is just random. That's not the point. I don't mean to draw this graph perfectly. The point I'm making is that when that coefficient of the quadratic term is positive, your quadratic function graph is going to look like this kind of shape, which means it's going to have a minimum point. A minimum point, so this is the case. In this case, we have a minimum. Okay? So, then they say find the coordinates of the vertex. Well, just like before, we're going to use this formula. H comma k, remember the formula for that, it has this formula, minus b over 2a, comma, the function at minus b over 2a. Okay, so we're going to find that. X is equal to minus b over 2a, which is, in this case, let's write this down. A is equal to 1/2. B is equal to 2. C is equal to negative 14, right? So let's plug in. Minus B is 2 over 2 times A, 2 times 1/2. So what do we end up with? Minus 2. 2 times 1/2 is 1. So minus 2. So this is our x component, or h component of the coordinate of the vertex. So now let's find y. How do we find y? We replace x with minus 2 in the original function and find the value of function at negative 2, which is that piece. That piece is all it's saying. Find this quantity, minus b over 2a, and then substitute in the original function. So the function at negative 2 is equal to 1/2 times minus 2 squared. I'm just replacing x with negative 2, plus 2 times minus 2, minus 14. So we have 1/2 minus 2 squared is 4. 2 times minus 2 is minus 4, minus 14. Okay? So let's distribute 4 times 1/2 is 2, minus 4, minus 14. And we end up with, so that's minus 18. Minus 18 plus 2 is minus 16. So this is our y component. So we have the x component and we have the y component. So the vertex is at negative 2 comma negative 16. Like that. Okay? And we know that this is a point of minimum. Okay, I hope this is in agreement with the solution you had. If not, and if you have questions, please bring them up to me. and we have come to the conclusion of another section 3.1. Thank you for persisting through this video, and for now, have a nice day, and I'll see you next time.